Now, in this session, we discuss Maxwell's velocity distribution. So, Maxwell said that for the given gas molecules, we can have a distribution of velocities, means three different velocities can be classified for the gas molecules. One we have already studied, that is called RMS velocity, and apart from that, two more velocities can be calculated for this one, so that the velocities of the gas molecules can be accommodated into these three categories. So first one is, you are not deriving it, you are just by hearting it. The first one is RMS velocity. RMS velocity. That is root mean square velocity. So that we found that VRMS is equal to square root of 3RT by molar mass. And another velocity is the average velocity. Average velocity. And this average velocity, V average, can be equal to square root of 8RT by pi into molar mass. Average velocity means simple thing, that is average of all the velocities associated with the molecules. Simple average. Okay. Adding all the individual velocities and dividing with that much numbers of molecules, okay, gives you the average velocity of the gas molecules, right? And the third one is that, is the most probable velocity. Most probable velocity, that is VMP, most probable, will be equal to square root of 2RT by molar mass. Most probable means if you are listing the velocities of the molecules, all these individual velocities, if you list there, in that list of velocities, which is the value which is repeated most, is called the most probable velocity. For example, if I list it like this, 1 meter per second, 2 meter per second, 2 meter per second, 4 meter per second, and 2, 3, okay, 1, 2, right? Like this, if I write, out of this listed numbers, which is the number repeating most, is called 1. See, 2 is the number which is repeated. 1, 2, 3, 4. Okay. Then 2 will be the most probable velocity for this listing of velocities. Understood? So, these three, RMS velocity, average velocity, and most probable velocities are the three different categories of velocities you can have here. Alright? Now the values of these three are found to be very close to each other, that all this RT by molar mass is common, and therefore here it is root 3 coming, and here it is root of 8 by pi is coming, and here it is root of 2 is coming. So, if you find the values of this one, they are very close to each other, so it comes the kind of a distribution in a graph form. Okay? If you take the graph of this velocity distributions, right, it comes like this, that the three velocities will be coming very close to each other. Alright? So we call it as distribution of velocities. Alright? Now, this is the equations that you are supposed supposed to by heart. And next comes a most important statement that is called equipartition of energy. Two more points. You can have equipartition of energy and number of degrees of freedom. First one, equipartition of energy of the gas. So what is equipartition of energy? It states that the energy associated with a gaseous system can be divided equally among the number of degrees of freedom, and each degree of freedom must get an energy of half RT per mole or half kT kb into T per molecule. So total energy is divided equally among number of degrees of freedom, and each degree of freedom must get an energy of half RT per mole or half kb into T per molecule. That means the energy associated with gas will be the multiple of, integral multiple of what you say, this values. Okay, into number of degrees of freedom. So, what is number of degrees of freedom? Number of degrees of freedom. Number of degrees of freedom means what? In a simple sense, we can take it as the number of different ways in which the total energy can be divided into, depending upon the state of the molecules of the gas. Okay? This is the number of different ways in which the total energy of the gas is divided into, depending upon the state of the molecule of the gas. Now, what is the state of the molecule of the gas? That to be understood. See, certain conditions, the molecules will be having only translatory motion. So, only translatory motion means translational kinetic energy you can have. In a volume, a three-dimensional space, you can have three different velocities along x-axis, y-axis and z-axis. Therefore, translated kinetic energy, you can have it in the x direction, y direction and also z directions. Alright. Now, in certain case, molecules will be having translatory motion. Along with that, there will be rotatory motion also. So the energy division is increasing, and in higher energy state, sometimes the molecules will be having translatory motion, rotational motion and also vibratory motion. So like this, the degrees of freedom can be changing according to the state of the molecule of the gas. So as the number of division of the energy is increasing, means the number of degrees of freedom is increasing. Understood? So while we are defining this equipartition of energy and also number of degrees of freedom is actually to calculate the adiabatic constant of the gas. Now, to find the number of degrees of freedom, we can have a formula here. That is, number of degrees of freedom F will be equal to 3 into A minus X. A simple mathematical formulation you can have like this, where A is called atomicity of the gas. That gas can be monatomic, diatomic or triatomic, that is called atomicity. Then X means number of independent relationships between the between the atoms of the molecule you can consider. Number of independent relationships. Okay? So, how to calculate the number of degrees of freedom for monatomic gas? Monatomic gas. Number of degrees of freedom will be 3 into monatomic minus nothing to relate, therefore number of degrees of freedom is 3. Monatomic gas. And for diatomic gas, this can be of the form, diatomic gas will be of this shape, the physical form of it, diatomic. So here you can have 1 and 2 atoms, so one relationship you can consider. And therefore, number of degrees of freedom will be equal to 3 into 2 minus 1, that's equal to 5. Okay? Then, if you get considering triatomic linear molecule, triatomic linear molecule means like this 1, 2, 3. Then the relation will be 1 and 2 and 2 and 3, but 1 and 3 is not permitted because in between 2 is coming being linear. So here the number of degrees of freedom will be equal to 3 into 3 minus 2, that is 7 it comes for triatomic linear. Okay, 3 into 3 9, 9 minus 2 7. And triatomic non-linear, if I take, will be of this form, a triangular shape you can have 1, 2 and 3. So we can have the relationship like this, and therefore here the freedom will be 3 into 3 minus 3, that is 6. So this is how we are finding the number of degrees of freedom for the different types of gases: monatomic, diatomic, triatomic linear and triatomic non-linear. So these values are important for calculating the adiabatic constant of the